Okay. So to kind of continue where we left off before the printing chaos started, um, what we were covering at the end was that sort of you have this idea of the simple model and the real experiment, and it's often not so easy to make the jump between sort of a simple example like a coin flip and what actual experimentation you're doing. And sort of one of the main differences you have in real experiments is this kind of idea of systematic variations. You know, when you're flipping a coin, you don't really expect the way that someone flips it would massively affect the result. But when you're performing a scientific experiment, the way your thermometer measures temperature could very clearly affect the final results that you're looking at, or the way that your camera is able to sort of differentiate between bone tissue and marrow or soft tissue could clearly affect the kind of results that you would get, or the sort of beam profile and your ability to correct it, or any number of other problems that could come up. But that basically with these real experiments, you have to be a lot more aware of this kind of stochastic variation and systematic variation. That, you know, the standard expectation that everything disappears as you do more and more experiments isn't always true. You know, that there are many cases where doing more experiments will actually start hurting your results because of sort of these systematic errors will become much, much, much larger. You know, if you look at a camera sensor whose performance is related to temperature, and its temperature is controlled by how many images have been taken, you know, if you do more and more experiments, at some point, basically all you're measuring with the camera is noise because it's heated up so much. And this isn't actually helping you understand anything about your sample. And if you include it in your results, you might be washing out any real signal you could be looking for. So we'll take an example here for this data set called Iris, because coin flips are very simple and not really very interesting. I'm not sure why the figure doesn't load in. Anyways, but basically the data set is like this, is shown in this table, and it's a number of different flowers. And so it's kind of an analysis you could imagine we've done before, where you're able to take a picture of a flower, you segment a bunch of features, and then you measure something like the sepal length, the sepal width, the petal length, and the petal width. And that you end up with these different classes for what species of flower this happens to be. And so based on these parameters, your goal is to kind of identify what species it is. And this is a kind of very common data set to use because it sort of more resembles these kind of experimental science results. Yeah, we'll look at the data set in more detail later, but that will be kind of what we'll use to do this analysis that we talk about. So for reproducibility, it's a very, very broad topic. There's lots of different subcourses on this that are linked to on the website as well. And we sort of mean two different things, or two main things, when we talk about reproducibility. And so the first one, kind of the most obvious one, is this idea of analysis. And this means for the image projects we do that we're going from image to numbers in a sort of clear manner that anyone anywhere could follow and get the exact, with some tolerance, same numbers as you did. And so what it means is that, you know, you can't have platform dependence, you can't have proprietary in-house algorithms, you can't have manual quicking, tweaking, copying. You know, you select the biggest object by drawing a circle around it, or you select the part that's bone by drawing a circle, and, you know, one script to go from the images to the final results. So if you take these criteria seriously, there's probably maybe fewer than 1% of scientific publications are actually able to fulfill all of them. But it's kind of the goal and the definition for what really reproducible work means. And so it means that anyone would be able to get the same results even if they had very different systems, preferences, feelings about the samples than you do, because you don't have any dependence on software or human interaction. And that you have sort of one clean way from going from the beginning to the end. So there's also no possibility for something to get mixed up. That when you look at a lot of ways studies are done, particularly in medical environments, there's copying and pasting of numbers from one program into an Excel table, and then the Excel table's exported and imported into SPSS, and then some other analysis is done, and then the paper's copied and pasted, or the results are copied and pasted into Word. And so at any point along that process, something could have gotten mixed up. Someone could have copied the wrong table, one of the columns might have gotten switched, and all of your results would be completely wrong. And if you follow these standards, of course, there's still the opportunity to make mistakes. But if you have one script to go from the image to the result, someone else can look over this and say if they see any mistakes there, and sort of assess it for how viable it actually is. If you copy and paste everything yourself, there's no way for anyone else to kind of look into this process and understand what you did. The next aspect for this is then sort of the measurements. This falls much more on kind of the experimental side, and that this idea is that so everything for the analysis plus taking the measurement several times, so we group this whole thing together, does not change the statistics significantly. And so here, we're not really focused on sort of, what exactly is the noise profile of your detector or the beam profile of your machine or any of these specific questions. It's much more of, if you take the same sample, rotate it a little bit, measure it on a Tuesday instead of a Monday, measure it at a synchrotron in Italy instead of a synchrotron in Switzerland, and run your analysis, do you get the same results or do you get significantly different results? And so you want to make sure that you're not doing an analysis that assumes, that your bone is always perfectly perpendicular to the field of view, or, where noise causes the threshold to be set in completely the wrong place, or that the illumination profile can change the number of cells that you find. You want to be as independent of those factors as possible. So in terms of kind of reproducible analysis, the basis for reproducible analysis are sort of scripts and macros. And so if you look at MATLAB, Java, R, Python, all of these tools, they have ways of running all of the analyses in sort of an automatic way. So what this means is that there's kind of one command that you execute and that no clicking or any interaction is required for you to get the final result. This also applies to notebooks, and we'll cover that in a little bit. So when we go back to this data set that we had of iris, one of the things we want to look at is how well can we tell different species apart. If we measure different species of flowers, and here we have 3 different groups, how sensitive is a metric like sepal width to this grouping that we have? And so if we take, this approach, we can make a plot like this, where we see the species on the x-axis. The exact x position doesn't mean anything. It's just spread out to show all the different points that come in. And the y-axis shows the sepal width. And what we see when we look at this is that, the differences between groups and the differences within groups is fairly similar. We see that there's differences here, but there's points like this which are in the setosa group but fall below the average for the versicolor group. And so that would be very difficult to identify as the setosa, and sort of vice versa. We then could look at something like petal length, and we see that there's kind of high group similarity, so that when we were to look at petal length, it's very clear that if you compare the measurements from this one to this one, that you would see that these groups are very clearly distinguishable. And so that, if you were measuring this petal length on a number of different flowers and you were to see that it was 4, you could be fairly confident that that was meaningful. And so what we have for doing this is this idea of this intra-class correlation coefficient. And it's kind of defined in this fairly basic way, where you sort of have this SA squared term on the top, and that's the variance among groups or classes. And it's kind of, the standard deviation of the mean values of each group. And so, what is the difference between the different groups that we have? And the SW is then the variance within groups. And so if you go within each group and look at the standard deviation, how big is it? And so if you have a value here of 1, that means that kind of 100% of the variation is between classes rather than within classes. And if you have a 0, that means 0% of the variation is between classes, and all of it is within classes. And so having a 1 means that your metric, sort of as we showed before, is very sort of clearly indicative of which group that you're in, that your parameter is quite sensitive to that. And having a 0 means you're closer to this, where the variation within each group is as big as the differences between groups. And so for this coefficient, what this helps us do is start to assess how sensitive is our metric at letting us measure what we want to measure in our samples. That if we were to look at this example and we were to say we can perfectly classify, different species of flowers based on sepal width, you would look at that result and say, I don't think that's very likely. It looks like there's a huge variation here. There's a lot of noise or whatever it might be in your system, causing it to be difficult for you to assess differences that are very subtle. Maybe if you had a more accurate measurement, or maybe if you were more consistent at finding the sepal, you could do this better, but that currently your measurements are far too noisy to try to differentiate that well. Versus if you were to look at a metric like petal length, you would see this and say, this seems like it's fairly reliable. There's clearly some standard deviation here. There's some variance in the values, but it's small compared to the difference between the groups. And so that's why we have this very simple metric of interclass correlation, where you don't really need to assume a model for your system or decide, what kind of classifier you're going to use. You can simply come up with a single score that shows you how reproducible your results are. And so so when we look at this first group, it's 0.5, and we look at this grass group, it's 0.96. And so exactly what you do with this depends on kind of what your study is based on, but it's usually a good metric for picking variables that would be useful to investigate in more detail. And so if you have hundreds and hundreds of variables, you'll want to focus on the ones that have high ICC scores, because that means you're not only able to measure them accurately, but that the measurements actually seem to separate groups fairly well. We'll skip this. I think it's not as useful for coin flips. Now, looking at sort of comparing groups. And so once you've done this initial step of, these variables could be interesting, this ICC score is very high, we can use it for another analysis that we're trying to do, you can now go to try to compare the groups that you're looking at. And so the idea is fundamentally to try to assess the likelihood that the true groups that you have could have been sampled from the same sort of master group or the same original set. And so the process for this is to kind of list the assumptions that you have and then kind of establish what your null hypothesis would be. And so this is one of the kind of most important parts of performing these statistical analyses, is coming up with sort of what's your basis, what are your list of assumptions that everything's based on, and what is the null hypothesis. And usually your null hypothesis would be that the groups are the same. And so that if we look at, this simple graph here, your null hypothesis would be that the sepal width is kind of independent of species. And that your goal by performing this test would be to show that, in fact, it's very unlikely that just randomly picking kind of flowers, you would get these observed differences if they came from the same group, if the species variable didn't really mean anything. And so what we calculate here is the probability of the observations, so the samples that we take, because we, as we covered before with kind of the coin flip, what we actually see there isn't the reality. We don't have a probability at the end. What we have is a sample of a coin flipper, and a coin. That's the only thing we're able to get out. We never get kind of we assume this tells us about the coin itself, but it doesn't actually represent the probability of the coin. It just represents a bunch of samples. And so what we try to calculate is what are the likelihoods, or what's the probability we would see these samples given the truth of the null hypothesis. And so it requires a knowledge about the probability distribution of sort of the data. How likely is it that you get a heads or a tails? Are these results completely independent? And the modeling can be very, very complicated. And so if you're not dealing with something as simple as a coin, where you do have events that are connected or related to one another, this is a very complicated task, which requires much, much more time than we can get into in this class. But that basically, if we look at the loaded coin as the example we take, we have an assumption. Our assumptions are we flip and observe flips of coins accurately and independently. The coin is invariant, so nothing about the coin is changing with time. Flipping it doesn't make it hotter, which causes it more likely to be heads or something, that it's entirely invariant and our experiments are sort of meaningful, and has the same expected value. So once we've established those as kind of our baseline hypotheses, which makes kind of this test that we're doing reasonable, we can then come up with a null hypothesis, and that would be that, the coin is unbiased, and so the expected value is 0.5. And so now we can calculate the likelihood of a given observation giving the number of flips. And so if we have one flip that's heads, the likelihood of this observation, if the coin is unbiased, is 50%. And so seeing a heads is 50% likely, which is exactly what we'd expect. If we have 5 heads in a row, the likelihood that we'd get 5 heads in a row, if the coin is unbiased, is 3%. If we now have 10 heads in a row, it's 0.1%. And so now kind of the question comes back to what we were originally looking at, was how good is good enough? How do we decide what threshold we cut off at to say, how many heads in a row do we need to see to reject this null hypothesis? And so what's important is that we're not proving or saying that the coin is biased. All we're doing is saying it seems very unlikely that the coin is not biased. And that's a very different statement to make. And so here we're not able to prove the coin is biased or anything. We're simply rejecting the fact that it's not biased. And so this is where we have this idea of sort of a student's t-distribution. Since we don't usually know the distribution very well, and the distributions can be quite complicated, we kind of can use this student's t-distribution where we assume the distribution of the variable we're measuring is normal. And the t will then give us an estimate for the mean of the underlying distribution based on a few observations. And so what we're able to do with this kind of student's t-distribution approximation is say that even though we don't perfectly know the distribution, we assume it's normal, and we can use this to model what the mean of that would likely be, so that we can establish how likely the observations we have are. And so when we come up with our set of assumptions initially, we have to assume unbiased observations and normal distribution if we want to apply the student's t-test to what we're doing. If we can't assume these things, we need to apply other tests, but this is by far the most common test that gets applied. And this is sort of a assumed or a requirement that you have if you want to apply these things. And so if you know, for example, your distribution is biased, then you'll have to choose a different test. Yeah?
Is a Gaussian distribution just a subset of the t-distribution?
Well, Gaussian is normal. Gaussian and normal are the same.
Okay. And how does normal correspond to the t-distribution?
So the t-distribution is if you have a few samples that come from a normal distribution, a t-distribution helps you model sort of what the mean of that normal mean and standard deviation of that normal distribution would be. So the t-distribution helps you figure out, if you see 5, 7, and 3, how would you approximate what the mean of that distribution is? I mean, the mean of that distribution could be 1,000,000, and you just happen to see 3 outliers in a row that were very, very small. And so what the t-distribution helps us do is take a few observations and model what the distribution probably looks like if it were to be Gaussian from those observations, which then allows us to make the link of, if the average were 1,000,000 and we saw 3, 5, and 7, this is a very, very unlikely event. It's not impossible, but it's unlikely. And so that's really what this helps us do, because when you take samples, when you do an experiment, all you're doing is measuring observations. You're not actually measuring the distribution itself. And so it's how do you go from those observations to an understanding of the distribution. So where this becomes very, very problematic with the t-test, which is another thing you'll hear very frequently as feedback when you publish papers, is this idea of multi-testing bias. And so the scientific community has kind of decided that a p-value of less than 0.05 is good enough for publication, which means if we get 5 heads in a row, we're good. We're at this 3.1%, a p-value of 0.03. And so, if this is the case, it's quite easy to have everyone in the class flip a coin 5 times and say, okay, if one of you gets 5 heads, then we have a statistically significant finding. That was a rare event. We've now found it. Does anyone see a problem with this? Right. Because it's now not the probability that one person got in 5 heads, 5 flips, 5 heads. It's now the probability that, 20 or however many people come get 5 heads in a row. And so if we look at, if you have a bunch of friends or a bunch of people in your class flipping, and you have 20 people flipping, the chance that one of them gets 5 heads is 47%. And so clearly, if that were your only requirement for being significant, this would be a complete failure on this. You could also go and say, okay, well, I will keep flipping my coin until I get 5 heads in a row. And that's also a p-value, according to this value, below 0.05. And that's the same idea, that you're basically not performing one experiment where you see how likely this result is. But if you keep flipping, you're almost guaranteed at some point to get 5 heads in a row. It's actually very unlikely that you'll get, heads, tails, heads, tails, heads, tails, perfect. You're going to see some variance there. And so fundamentally the problem is that when you have this initial model, your assumptions here are you are only flipping the coin 5 times. There is only one person flipping. And if one person flips it 5 times, that's a very rare event. And when you have a number of people flipping it, or someone flipping it continuously, you end up very quickly in this regime where you're not actually measuring what you say you're measuring, or you're not doing the experiment you said you were doing. And so while it might seem in your head that flipping a coin forever until you get 5 heads and saying, look, this is a very rare event, is the same as flipping it 5 times and getting 5 heads, it's in fact completely different. And so this is where this multiple testing bias comes in, because you have this idea that when you're measuring these probabilities, they're built on a fixed experiment under a fixed circumstance. And they're built on exactly one experiment. And so as you start changing these boundary conditions, you violate what the actual meaning of this p-value is and the significance of the result that you have. And so the standard way to correct this is simply by kind of dividing by the number of experiments that you did or the number of tests you performed. And so, if you were to flip if you were to have 10 friends flip, then you would just divide the p-value by 10, and that would get you a significant result. And so that would mean that it would be, if you're having 10 friends flipping coins, you'll probably have them get 10 heads in a row rather than 5 heads in a row. So this is a bit of a difficult concept to kind of feel comfortable with. You sort of have to, I think about it a fair amount to appreciate sort of the subtlety of why these differences are important. But this is a critical idea to understand, because if you don't understand this, it's very easy to publish or be convinced by results that aren't in fact interesting at all. So where this really becomes problematic is, for us, we've covered so many different things that we can quantify in samples. If you remember the shape analysis lecture, we have this RegProps function, or we have this texture analysis in 9, where we can get easily 75 different metrics for every single object we measure in our image. And so each one of these metrics we can summarize in different ways. We could look at orientation, we can look at size, volume, perimeter, edge, any of these factors. And we'll have tons and tons and tons of different metrics we can look at. For a single cell analysis study, you could have over 1,000 different parameters that you're measuring. And if we were to say we're looking for a p-value in a single experiment of less than 0.05, and we have sort of 10 samples in each group, how does increasing the number of variables in our study affect our results? And so what we see here is that, if you go to 60 variables, on average, you'll find 3 of them to be significant. And this isn't an actual study. This is just if all of your variables are complete noise. So just completely randomly sampled distributions. And you have 60 variables, and you do what we did before with the p-value less than 0.05, you'll end up with 3 that appear to be significant. And so what's the problem with this? I mean, should everyone just measure more and more and more variables because then you're more likely to get a significant result?
One should correct the number of variables so far generated.
Yeah.
But I mean, there's promises that variables might not, if we assume that the variables are independent from each other.
Yeah.
But when they start to be correlated to each other, it becomes more complicated.
Yeah. The correction becomes slightly more complicated that you have to do. Yeah. So we don't get into that very much. But yeah, if you are covering variables that are very strongly correlated, how you deal with the correction factor changes slightly. But that basically what we see here is that we need to somehow correct for the fact that we did 60 different tests. And that doing 60 different tests isn't the same as doing one. And so the likelihood of finding something significant goes up. And so what we can do is we can just sort of correct by the number of tests performed, where we now end up with the corrected graph below, where the likelihood of number of significant findings we have kind of stays constant because we've made it more difficult to have a significant finding. So we've increased our p threshold by doing this correction. And so that seems like a fairly good result. Can anyone think of why that might be problematic? Just dividing your p-value by the number of experiments you did? Yeah? Exactly. So by making this correction factor, if we did have a group that was different by 5%, and we now divide our threshold for finding a significant result by 60, or multiply the result we get by 60, either way, it makes it 60 times harder for us to find a small difference. And so this is sort of where that important factor comes in, where we have kind of this graph here, where we have sort of one variable with a shift of one standard deviation for the other. And if we have sort of a small number of samples in the study, we can see sort of what the p-value for a 10% difference would be. And as the number of samples goes up, that p-value sort of goes down. And as we start increasing the number of variables we check for, the probability of us actually finding this significant difference goes down. And so if we have 100 variables we're looking at in our study, and we only have 25 samples, the likelihood that we see this difference is 10% or 5%. And if we only had one variable, the likelihood we'd find it is 50 or 60%. And so as we sort of add more samples, add more variables, we're forced to correct. And this correction makes it harder and harder to see the differences. Yeah? Yeah, this is the Bonferroni correction. Or Bonferroni is just a fancy name that has some more statistical details in it, but the correction is fundamentally the same. But that what you see with this is that if you have tons and tons of data, so if you had 125 samples, it actually doesn't make that much of a difference. You're likely to find the significant difference either way. Also, if the difference is big enough, you'll find it as well. But if you're looking for small differences, and so if there's one gene in your body that makes you 5% more likely to get breast cancer, and you test 1 million genes, the likelihood that you'll notice this one gene is very, very, very low. But if you're able to say this gene and this other gene looks suspicious, we want to look for that in detail, your likelihood of finding it is much higher. And so what this practically means for when you're doing these kind of studies and experiments is that you need to be very careful with what variables you test, because each variable you test costs something. So each additional variable you include in your study means it's less likely you'll see a small difference in all the other variables you want to look at. And that if you go and say, we'll put all the variables in, we'll see which ones have statistically significant results, then we'll throw out all the ones that didn't and just look at the statistically significant ones and then only do the Bonferroni correction for the ones we kept, that's complete nonsense. And so that's what we had back here, where you basically just, this would be taking these 60 random variables, finding the 3 that were different, and then keeping them. Even though we know, because this data is generated, that none of them are significant at all. They're just all randomly sampled numbers. But by chance, 3 of them are likely to sort of pass this 0.05 cutoff. And so here we kind of see that we're required to have a lot of discipline with the sort of tests that we do. Otherwise, we'll end up kind of contaminating our data. And so you don't want to perform t-tests on lots and lots of things, because each one you perform has a cost. You sort of have to carry it with you and remember that you've already tested 100 variables before. And so even though you're only testing one variable now, you have to include the 100 you tested before in order to be confident that you're robust against sort of noise. This is also one of the reasons there's a lot of arguments about making the p-value higher. And so if you made the p-value 0.01 or 0.001, you would have to worry about these multiple testing issues less, because it would be a lot harder to run into areas where you have issues, because you need to do millions of tests. Yeah?
But this is only the case if you vary all your variables at the same time. So if you keep some variables constant, you increase the probability that you find a difference.
Well, so in this case, these are measurements. So these are variables coming out of your system. So if you're measuring the bubble size, and then you're measuring bubble anisotropy, and then you're measuring bubble volume, and then you're measuring bubble length, and then you measure bubble surface area. And if you were like, I think any of them could be interesting, and so I'll test all these 10 variables, you're making it that much more difficult to see an actual difference when it takes place. When you're performing your experiment and you're controlling temperature, it's sort of a different thing that you're looking at. Yeah?
What if you're trying to discover what variables are relevant? You just do this, see what passes, and then do another test on those specific variables?
You shouldn't do that. So that's where you run into problems. That if you do this on every variable, you've kind of contaminated that data set already. So you could do this on every variable and say, these are the variables that look the most interesting. It would be interesting in another study to investigate if there's a relationship between, bubble size and temperature or something like that. But that once you've done these 1,000 t-tests or 100,000 t-tests, you've contaminated your data. You can't use it as if you hadn't tested anything on it before.
But can't you just run a new set of experiments?
You can run a new set of experiments and collect new data, and that's fine. You just can't reuse that data to test those hypotheses.
So is that the standard way to find, if you're just doing data discovery, you're trying to find out what variables are relevant to you?
Right. So you could do that on all the variables and kind of see these look interesting, but you wouldn't call that a t-test. You might use the t-test function and use the p-value as kind of an indicator to make a nice picture, but you wouldn't actually be performing a t-test, I guess, would be. The actual analysis you'd be doing would be very different. I mean, so that's sort of, like with the spurious correlation aspect, if we want to bring it back to this problem, you can look through millions and millions of variables and find these correlations. And if you wanted to show that there was actually a link between them, you can't use this data anymore. It's already contaminated by the fact that you've looked through everything possible and picked out interesting correlations. And so what would you have to do to actually test this? If you wanted to show that hanging and suicides were related to spending on science? Yeah?
Look at a new country or something.
You could look at a new country, or you could measure in the future. And so when you're validating things in time series models, you usually use a time in the future to ensure your model, if you train it from 1999 to 2009, you would test it on 2009 to 2018. And so if you came up, this looks like an interesting correlation, you can't now say it's an interesting correlation because the factor is 0.999 and we searched through 100 million variables until we found this. If you wanted to show that this was interesting, you'd have to go from 2010 and test this on that data. And maybe, unfortunately, you might still see a correlation there, and then you would have to sort of explain it, but in all likelihood, you'd probably have no link anymore because there's no reason to expect that those two things would be related. But that once you've done this searching, you can't now reuse this data to show, look, this is an interesting result and I prove it with this data set. That it's already completely contaminated and you can't do that analysis anymore. And I think if you were to do a statistical analysis on this, you would very quickly show that this is not a significant finding because you looked through millions and millions of different variables. And so your Bonferroni correction factor is so high that nothing you find would be significant, or almost nothing you would find would be significant. Yeah.
Would it be part of a good approach? Let's say, so already in the beginning we talked about dividing data sets into training and testing.
Yeah.
Testing data sets. So would there be, say, another category now where we would perform exploratory analysis? Right from the start, we allocated another chunk.
Yeah.
Where we look for all the variables that might be interesting, perform tests so that they actually look like something interesting to look at, and then proceed to actually testing and
so that's
training and testing.
Yeah, so that's exactly the kind of that same approach that you have of sort of dividing your data up into this is a training group, this is a testing group or validation group or whatever those other different categories are called, which we'll get into a little bit here. Works well for these kind of analyses too, because sort of with a neural network, what you're doing is you're feeding a ton of data in and it's finding a bunch of weird correlations, and that you have another group of data that it's never seen before, where you test to see if the weird correlations it found are actually any useful for solving your problem, or useful at all for solving your problem. And so that you can kind of think of, when you have these complicated models or, SVMs or neural networks or whatever they are, all they're doing in your data is looking for interesting correlations. And that if you do that on one group and then take another group, you can't use that group again to see if it's valid because, of course, it will find the same interesting correlations in the same group. But if you take another group that you haven't contaminated yet, it will show you if those correlations actually hold through in your data set. So many of these ideas are very transferable. But yeah, it's probably a much better idea to take a small portion of your data and play with it and then use another set to actually validate it. But you'd want to make sure, like with the time series examples, if with the time series data, you can't then, use these 2 years, 2006 and 2007, to validate it, because kind of almost by definition, they'll be between these 2 points. And so you'll want to use something that's kind of going in the future in order to be sure that that works. With non-time series data, what that would mean would be you'd want to make sure your experiments were done on different days. The image formats were, the manufacturers were different, or whatever other variables that you have that commonly change are different between those 2 groups. But that's, of course, a whole challenge for itself. So the part we'll get into quickly here is this idea of sort of predicting and validating, which we've already covered. There's this very useful graphic from scikit-learn, where they kind of show you how you deal with a prediction or learning problem. That, if you start, how many samples do you have? Are you trying to predict a category? Are you just looking? Are you trying to predict structure? Are you trying to predict values, and what tools make sense in what area? So a lot of this we've covered a little bit before with sort of our supervised approaches, and this just sort of reiterates it and summarizes it in a nice graphic. But yeah, we have this idea that we mentioned before of kind of overfitting, where it's easy to have things that give you perfect results or appear to give you perfect results because they're overfit. And that's why you have this important set of sort of validation, of separating training, validating, and testing data so that you can understand what your models do well. And if we go back to the classifying flowers problem, that we can basically take the data that we have and split it up so that we have training, testing, validation, and then we can do something like build a simple decision tree where we try to classify, what species of flower it is based on the sepal length and the sepal width, and you get this yes-no model to classify what species you're in, and then you can predict and then overlay the actual results with it. And so here, the small points are correct, the big points are incorrect, and we can show what our decision tree did on the prediction data. So it did fairly well on the data it was trained to work on. And if we take it to the data it's never seen before, it does okay on some of the points, but it makes a lot of mistakes. And it makes a lot more mistakes than it did on the original data, and so it probably didn't fit it very well. And if we take sort of the test data, normally we wouldn't look at this until the very end. We see it got some of them right and it got some of them incorrect. We can get to sort of a more tricky example. And so this one, you have sort of these two spiral patterns, and you're trying to classify sort of happy and sad points, or whatever other classes you might want to define here are. And, how do you build a model to classify them well? You also have this whole TensorFlow playground where you can this one, playground.tensorflow.org, where you can click this model here and see, and so you can have how much of the data should be test data. And so here, the test data are the round circles for the validation data, and you can turn them on and off, and you can see sort of how well does it do at classifying the training data and how well does it do on the test data, and that you can run your model and see how well it learns to fit this spiral pattern, and sort of what weights are important for doing that. And that you see it initially, it has almost no idea what a spiral pattern is, and it gets very odd ideas in its head about what this pattern could be. But if you give it some more useful features, maybe more layers, or change the learning rate, or change still not very happy. I think eventually you can get this pattern, but I don't remember exactly how. But that anyways, you have a nice way of playing around with different models and seeing how much does sort of affecting the difference between your training and your test data, your noise in your data set. So right now the noise is 0. How big the batch sizes are that it's trying to group in. And here you see it coming up with very strange patterns, but it's potentially starting to get a better idea of what the data set looks like. And here you see the two scores comparing how well it's actually doing on the training data versus the testing data. So we can leave that running. We can divide that up into different groups. So here we have the training, validation, testing. We can build the decision tree like we did before, where you end up with something that clearly has no idea what your pattern is, but came up with an interesting rule for classifying it. But when you put in the validation data, you see it does very poorly because it hasn't actually understood the model well. If you put in more complicated data or more complicated models, it starts to get a slightly better pattern, but still it's very far away from what we consider a good model. So on the standard image processing chain, which we covered again at the beginning of it, we have this kind of problem that we have all of these different parameters. And this is something we talked about briefly before, where you have your images coming in, you have a Gaussian filter, a threshold, a shape analysis, a thickness analysis, and that you can end up with kind of all of these decisions you need to make and all of these parameters you need to choose in order to do an analysis. And how do you pick the best parameters or know what works well or have confidence in your results? And so we showed an example, here you see actually all the parameters that have to go in. Is your threshold 90, 100, 110? Is your sigma 0.5? Is it a 7 by 7 neighborhood, a 3 by 3, a 5 by 5? Kind of all of these problems and different things you could try to explore. And we see that it's over 180 combinations for just one sample. And to calculate for one sample could take days or weeks. And so it's clearly quite time consuming. How do we start to do this well? And so one of the examples we mentioned before was this computer vision, which I'll add to the course lecture, where we have sort of this pipeline where we're trying to decide, we put an image in, we want to segment cells out, and we know, we want to use a Gaussian filter, we want to use some dilation, some erosion operations, how many times should we use them, what's the size, that we can kind of define this pipeline with all the parameters that are important for it, and that we can use this SciPy optimized fmin, or if you're in MATLAB, the fmin search function, where you basically say, what are the parameters you want to look through? And it will randomly try guessing different parameters until it sees kind of a trend. And it will then follow the trend that it sees. And so that's a gradient descent approach to try to improve what this intersection over union is. And so if you go up to the top, it's basically trying to come up with the best approach for segmenting these cells. And so since we know roughly what operations go in, we can have it optimize those operations so that it comes up with a nice prediction for where the cells are in the image. And so this is a fairly simple pipeline, but you can do this with much more complicated ones where you basically, if you have ground truth, you can have it search for what the best values for this are. So yeah, you come up with these different segmentations. You can do a qualitative assessment, but one of the more interesting quantitative methods you can use is this idea of a parameter sweep. And so you can do your full analysis over a number of different threshold values and see how, for example, your volume changes as you change the threshold value. And so, here you can look at the volume distribution, you can look at the orientation, you can look at any metric you were looking at before, and you can use sort of these ideas from control theory where you measure the sensitivity. So how much does a change in your parameter cause a change in your output metric? You can be a little bit more practical by looking at sort of, what's the maximum value of your metric minus the minimum over the average to sort of normalize it, because a lot of times the parameter units aren't very meaningful. If your threshold's 100,000, or your threshold 0, you don't necessarily want to divide by 0. But that what you can see is that if you had an object, if you were doing something like object count, and you saw that you sort of had this dip and rise again, that this would potentially be a good place to have your threshold, because there's not a whole lot of change that's going on in that area. You know that if your threshold's here and your noise is just a little bit, you're changing your object count by hundreds. And you want that to be sort of as smooth as possible. And similarly, you can plot different variables. So if you had anisotropy, count, and volume, you would try to pick a point where that is sort of as flat as possible for the curves that you're most interested in. So if you're mainly measuring anisotropy, then you'd focus on that. But if you're interested mostly in volume and count, then you'd focus on those values. So the last thing we'll cover is this idea of unit testing. And so this is the idea that everything that you write should be tested. And so what most of you have probably done anyways, manually, where you have sort of, you know, if you make a function in MATLAB or a function in Python that counts voxels, you'll run it on a couple small test images to make sure that it works well. And what unit testing is the process of making this automatic. So by coming up with a few basic tests that you run to ensure that every time you put a new data set in or run your algorithm, that it's automatically being tested. And so they often look something like this in MATLAB, where you have sort of assert statements to show that, you know, if you have a function that counts voxels and you give it an empty 3D image, it should give you 0. If you give it an empty 2D image, it should give you 0. And if you give it an identity image, it should give you 3. You know, is it actually counting voxels correctly? So of course, if you have a function called shape analysis, that's probably too difficult to use. You'll want to break it down into a bunch of smaller pieces that you can all test individually, because that makes it a lot easier to test as opposed to a whole shape analysis pipeline that you're running. If you use ImageJ, you can test with some of the ImageJ code they have. If you use KNIME, KNIME has test nodes built into it that sort of you can make a workflow where you're checking that differences are small. And so all the tests for KNIME are built using this. They also have disturber nodes, which sort of insert random or missing values to determine fault tolerance. And that what we have in Python are these tools called PyTest, which is sort of a full-scale testing package. And so if you go to scikit image, this uses PyTest to test it, where you make sort of these classes like watershed, and you have it, you know, you give it a test image of, you know, this array here with the markers here, and you show that it gives you the right expected result when you do this. And what advantage this has is now you very clearly defined what this tool is supposed to do, how it's supposed to behave in a number of situations. And if someone comes and says, I have a new great version of Watershed that's 100 times faster, then you can say, well, if it passes all of these tests, I'm confident that it works. And with this sort of testing framework, you allow yourself to kind of not have to manually check everything that someone does. You can have it automatically be checked by these components. What's probably more practical for you is this idea of doc tests. And so in Python, in MATLAB, and a lot of these different tools, you can have documentation right below your function. So when you have these 3 quotation marks, everything that comes below that is the documentation for the function that you're writing. And all this here is just text. There's different ways you can format it. So if you read Google's style guideline, they have ways they want you to write this documentation, but this is all completely free. Where it gets interesting is where you have these examples. And so whenever you have these three carets, three greater than signs, sorry, it will assume, if you're using doc tests, that those are code that you want to run. And so that you can say, here is a test image. If you apply this hysteresis threshold to that test image, you'll get this answer out. And so if you have 1, 2, 3, 2, 1, 2, whatever it is, you'll get that 0, 1, 1, 1, 0, 0, 1, 1, 1 out. And so that you have not only in your documentation a description of what the function does, but an example of some outputs that come out. And what doc tests do that make this sort of very interesting is that they find this text automatically and run it for you. And so if we go back here, this is a little block so that you can use it in notebooks, if this works. Anyways, for whatever reason, I probably have to restart the notebook. It's not showing up, but that you can have this code here where you say add 5, 5 should be 10. It finds the tests and add 5 if you have this little auto test before, which we defined in the above. And it says expecting 10, okay, the test passed. And so if we were to have 11 there, it would say the test failed, the function doesn't work. And the advantage you have with this is that while you're coding in a notebook, you can be adding tests to make sure that the functions do what they're supposed to do under simple circumstances. Of course, for images, this gets a little bit trickier. That if you wanted to, have a function called label an image, you come up with maybe a test image like this, where it's this identity, so this I 3 by 3. And if you perform simple label, you'd expect it to be, one component because they're all connected together. But then if you turned this pixel off in the middle, then you would get 2 components, so 1, 2. And so if you run this, it finds the tests inside of it and it goes through and checks to make sure that all of those values match exactly what you put into it. This also has the advantage that someone else looking at your simple label function can get a feeling for how you use it and what the inputs and outputs are. And so it makes it a lot easier to run into someone else's code and actually see that this is how it's supposed to be used, and these are some simple test inputs that make sense. Because as you'll notice, when you're using something like a label function on a giant 20,000 by 20,000 image, it's very difficult to see if it's doing something correctly or not. Because it gives a result that seems mostly reasonable, but if you have these tests, you can ensure that it's really doing what you expect it to be doing. And even when you're using label from scikit image, it might be useful to have these kind of tests for your stuff, because then you're confident about what it does in exactly this situation. Does it include diagonal elements when you do a component labeling, yes or no? Or does it, how does it deal with boundaries? Or how does it deal with images that are floating point instead of integer, or any number of other questions that if you have tests in your package, you can be confident that those things work well. Even MATLAB has unit tests, and so you can go to that link to learn more about what MATLAB does. You have this kind of idea of test-driven programming or test-driven development, TDD, where you run all of these tests. These tests kind of form the basis for what you're doing. So rather than saying, I'm going to write a function to do this really cool task, you say, I'm going to write a bunch of tests where shape analysis must give anisotropy of 0 when we input a sphere. It should give the center of volume within 0.5 pixels. It must run on a 1,000 by 1,000 image in 30 seconds. And so your job is to come up with these tests. And then someone writes code that is the simplest, easiest to read code that passes all of the tests. But that you basically kind of split up the task into someone is deciding what the tests that need to be passed are, and then someone builds the code that passes it. And basically, if you pass all of the tests, your code must be right. And if your code isn't right, that means the person who wrote the test didn't do a very good job of coming up with good test criteria. The last thing I'll mention in this lecture is this idea of continuous integration. And this is what we use for the class as well. So this idea of kind of dog fooding, that I use all the tools that I tell you to use yourself. And this is where you have every single time someone makes a change to your code, a tool online checks out a copy of it and runs all the tests and goes through all the different steps for building your package to ensure that it's correct. And so with the QBI lecture, this is what we do, and it goes through every slide, so every line of code in every slide, and makes sure that that code works. And so if we go to the course webpage, or the GitHub for the course, you can go to the commits, and you can see next to each commit, there's this little checkbox, or X. And so if you click on it, you can see circle CI, your tests passed. And if you go, it'll take you to the site. It'll say sort of what was run. And we can also go, I think, to Insights. Okay, for whatever reason, it doesn't seem to be working there. But that if we go back to the course page, you can see that there were some changes that I made. For example, this one, where it didn't pass. And if you click Details, you can see that it failed. And it did all of these things. But on one of the slides, what was the typo? In the dynamic experiment slides, I had a problem that this F underscore MSE was not defined. And so I didn't have it defined in the notebook, which meant that when it tried to execute all the code, it failed. And so also if you're in the course Slack, there's this sort of annoying bot that I just added to, I think, the random channel, where every time I make a change, we have this error checking box, which says that the build was successful or not, and everything that happened in it. And so automatically, every time something in this course is changed or some update is made, all of the slides are rerun to ensure that everything builds correctly. And if you look at the history, there are a large number, as this was getting set up, a large number of failed builds because the environments weren't correct, all the packages weren't installed, there were different versions of different packages, any number of different possible mistakes. But the advantage you have with this is that if you go to this is another one of the projects we have, where there's a bunch of code in this library that does a number of different things. And if someone wants to make a change, so here, if we were removing Spark support, that you could see someone made this change where they deleted this code from a file, and that all the tests were automatically run from Travis and Circle, and the Travis ones passed and the Circle ones didn't. And so you can look at that and decide whether or not to accept someone's changes because all the tests on all the code have been run, and you can see immediately if they broke something or not. And so when you go to open source projects on GitHub, almost all of them, or all of the good ones, have this set up. So if you go to scikit image and you make a change, and you say, I think label function should work on 12-dimensional images, it will make sure that the label function you made doesn't break everything that you've done for 2D and 3D images where all the tests exist. And so you have this sort of easy way of ensuring that all the important core functionality is being automatically checked and run. And one of the nice things about tools like Travis and Circle is if you have an open source project or you have your code on GitHub open sourced, you don't have to pay anything to use these tools. And so you get access to something that will run all of your scripts and run all of your tests for you for free automatically. And it makes it a lot easier for someone else to use your tools. Because if you know Circle and Travis is able to run all your code and pass all your tests, it should work for anyone else who's reasonably skilled. But if you don't have that, it might only work on your computer. And this ensures it at least works on whatever setup Circle and Travis have for you. But yeah, that's I think the last slide we'll cover for today, unless there's any questions on that.
I guess, in my experience, testing has been definitely very limited, but there's always this kind of friction that one experiences in the beginning. You start coding as you used to, and then you try to integrate this testing behavior that you stop, make a test, restart, and it is definitely, I guess maybe this test-driven development is perhaps the best approach in the sense that you think beforehand what should be the tests be, and then start coding and see that you fulfill the requirements of the test. Or do you see other models that make it convenient in a way to disrupt perhaps not completely your coding behavior?
Right. So we think, the Jupyter-based testing, I think, works quite well because it keeps you still in this interactive environment, but it allows you to build fairly good tests as you go.
But they have to be simple, right? Because I see a shortcoming of this syntax is probably that writing this kind of documentation
Does get, so if you have giant images, it becomes much more difficult. But for a lot of the things you're worried about, you can come up with fairly simple cases to make sure it's doing the right thing in those cases. You'll never be able to, test, does some giant neural network classify a dog correctly when you give it this picture? You could have that as a test, but that would be a very complicated, messy test to do.
by design, tests should be simple.
Right. But if you have a test that if you give it an image, it doesn't give you an error message, it would be a good test. If you give it a text file, it should tell you this file's not supported. That kind of thing where you kind of can be sure, or if you can think about sort of the problems you run into frequently. So if you don't have padding on your images, what happens, or what happens at a border? So if you're doing like a convolution on your image and you want to know, does it include the values at the border or not? The easiest image to do that in is a 3x3 identity matrix image, because you can calculate by hand what those values should be. If you do it on a 1,000 by 1,000 image, it'll be really difficult for you to see actually what happened. And by 3x3, you can still keep it visible, and you make it accessible for someone else looking at it, what that function does. And so I think by having like this docstring done well, you can cover a lot of the basic testing requirements as you work interactively. And so it takes some time and some discipline, but as soon as you start working with other people, it very quickly becomes valuable. Because then you never, particularly with this continuous integration, you never have this kind of excuse of it works fine on my computer. And you can be like, it works fine on Travis, which means it's your fault if you can't get it running. Go on, Stack Overflow and read about it. Versus if you don't have that set up, it could be the fact that your code's crap, or the other person doesn't know what they're doing, or they have the wrong version of some package, and all of those things get complicated.
But I guess there is such thing as this lazy testing, in the sense that, I run it on Travis, but in the end it just fails because there's some, syntax error or so.
Yeah.
It doesn't actually focus on meaningful tests.
Right. Or there's people who delete the tests that fail. So rather than think about why their new function doesn't pass the old tests, they delete the old tests or disable the tests. So if you go on like ImageJ, for example, the number of tests for ImageJ 1.0 goes down every year because he gets frustrated when he changes things and the tests break because someone else wrote the test as a summer of code project and deletes the ones he doesn't like. And so that's usually a bad sign, but it's still good to have this test because if you're having, I mean, even for your own documentation to know, like, why did you make a simple label function? There is already a label function. And if you have good doc tests, you can immediately see, oh, that's what it does. Versus I have to make an image and then I have to look at it and I probably have to zoom into a couple different parts to really study it in detail. Where if you can come up with these tests well, it makes everything much easier for you. And that particularly with sort of like neural networks, if you're building really complicated models, to just make sure, you know, when you put in this kind of input, you get this kind of output. That when you set it up, it has the right number of classes. If you give it the wrong dimension image, it gives you a reasonable error message. Because if you don't build in those error messages yourself, it'll tell you, you know, tensor 42 is incompatible with tensor 43, which isn't a helpful error message at all. You know, you can't fix the problem. But if you have something that's able to kind of pick out those things at the beginning and you make sure that that works, that makes your life much easier. And so I think that's where a lot of these things are useful, is that you can have sort of the core things covered fairly well and some confidence that they actually work. I mean, even with like image registration, as we talked about before, that's a very complicated problem. But, you know, registering an identity matrix to a shifted identity matrix, you know exactly what it should be. Registering a chest x-ray to a chest x-ray, you don't know if your learning rate's too high, if your optimization function's wrong, or anything else. And it's the exact kind of problem where you can build something in NumPy or ITK easily, but then if you want it to be faster and you want to implement it on the GPU, how can you be confident that the GPU gives you the same results as the ITK one does? And that by doing testing well, you can get that set up so that, you know, you don't need to do any extra work to make sure the GPU code is correct. But it's something that sort of requires active effort and often thinking about what kind of things you want to test well before. You know, that when we were coming up with something for trying to find lesions in the human body, you want to equally sample healthy tissue and sick tissue. And this sounds easy. You know, you just come up with a random generator. And then you start to realize, but, you know, sometimes, you know, this is in 3D. You don't want to sample space outside the patient, so it has to be kind of confined to inside the patient. Actually, you want it probably to be in the lungs or at the boundary to the lungs. And start coming up with something that does a reasonable sampling and gives you about 50% lesions, 50% healthy tissue is very difficult to do. And if you don't write tests, it might seem like you've built something that works well. But if you build tests on sort of less complicated data where it's just, you know, a box and you're trying to make sure that it samples equally inside and outside the box, or two boxes, or whatever the simple case might be, it's a lot easier to debug that and make sure it's working well. And so if you really want that to be set up right, it takes a lot more, it takes some effort to do. But it's, I mean, at least when we did it last week, we found probably 15 mistakes in this fairly simple sampling code that you wouldn't find unless you gave it really, really simple data sets and saw, oh, it's way oversampling this region because that's close to a border and it forgets to cut off the border. And so those kinds of problems come up quite frequently. But yeah, I mean, if it's not easy to do, I don't think people won't do it. And so I think the doc tests are the easiest way to sort of start. But yeah, so if there's